So for some logistics, assignment 3 is released, and we don't have enough material to, we haven't covered enough material to do assignment 3 yet, but you'll be able to work on assignment 3 problems after the lectures of this week is done. And after next week's lecture is done, you will be able to do the speech recognition problem in assignment 3 as well. But if you're interested in trying out assignment 3, you can start trying. And actually, last weekend, the codes were released on Saturday morning, and by Sunday morning, someone posted on Piazza saying that they have finished almost all of the assignment 3 already. So actually, assignment 3 took me like 2 days when I was doing that myself, but you guys are much faster at coding than I am. So assignment 3 is, yeah.
Can you speak a bit loudly? It's very difficult to hear on the channel.
Okay, sure. So is the volume okay now? A bit better, okay. So yeah, I will adjust the position of the mic. So the workload for assignment 3 is going to be a little bit less than assignment 1 and 2, but it is still a fair amount of workload. So in the starting script of assignment 3, there is a line that you need to change for bug fix. So please change use CUDA into use GPU. And if there are some other questions if there are some generic questions about assignment 3, please feel free to post on Piazza. And if there are some individualized requests, please email the assignment 3 teams. Yeah. Yeah. So it's the classify.py script. You can see the starting script at the CS server. So it's at the -u/cs401/a3 minbert.
Sir, is it classifier or classifier?
Classifier. Yeah, it's classifier. Wait, is that? I'm gonna double check on that.
Yeah, I think it's it is A3 minbert.
Yes, A3 minbert.
Yeah, I don't think I see a classify.py.
Yeah. Yeah, there's a typo on the slide. Sorry. So let's get to the contents of the natural language understanding. So natural language understanding is a topic that is under pretty heated discussions in recent years. So there are mainly two extreme directions of two arguments about natural language understanding. So on the more optimistic side, some people are saying that the very deep neural network language models are able to understand the language, and they can solve the language problems. And essentially, they are like intelligent systems that can behave in a similar way as humans. And you can automate some tasks and use the very complicated or advanced natural language processing systems to replace a large part of humans' job, including writing the homeworks, which I don't think is reliable yet. So actually, some problems are solvable by ChatGPT, but many others cannot. And in assignment 3, one of the bonus problems is requires you to plug in some questions of assignment 3 into ChatGPT and look at the result. And you can compare the generated contents versus the contents that you wrote yourself. And then you can make a decision of whether the ChatGPT answer generation is reliable or not. And in terms of the debate, there's a less optimistic side, which consists of many professors. For example, Professor Emily Bender at University of Washington claims that the current generation of natural language processing systems have no understanding of the language whatsoever at all. So they are just parameterized functions that can compute something based on the input, and the inputs can be the tokens or the embeddings of the tokens. So how in the world is that possible that you run some computations on the numbers and result in the functionality called understanding? So according to them, understanding is a functionality that occurs only in humans, and only humans are able to understand language at all. Question?
Sir, how is understanding, like understanding really defined here? Or what does really understanding really means?
Understanding, this is a philosophical discussion.
Yeah,
So
it depends.
yeah, it really depends
Yen
on.
Quinn recently have published something about this, like large LLM are just like things putting together.
Yes.
It doesn't really get any meaning of the word really.
Yes, yes. There are many levels of understanding. I will actually describe that in a few slides.
Okay.
So the actual range and the definition of the term understanding is very vague and is still under heated discussions. So in terms of this debate, I tend to take a position that is between the two extreme positions. So I think the current natural language processing system is able to understand some part of the language, but not some other part. So they have some ability that resembles the ability of humans in processing languages, but they are not able to do many other things that humans are able to do in terms of language. So in the remaining part of the week's lecture and tutorials, I'll describe some methods for building AI systems that can quote-unquote understand languages. So natural language understanding is a metaphorical term. So nothing is solid definition here. It is just a framework that studies AI systems in a way that is similar to humans. So why do we need a separate framework that is beyond the usual computation framework? So this is actually popular when studying the complicated systems. So as a side note, so in the physics, the similar frameworks occur as well. So in a macroscopic world, you can assume that most objects follow the Newton's 3 rules, and also in the microscopic world, you can assume that the molecules are rigid balls that can hit each other and transmit the momentums and velocities and this kind of and their behavior can be described by the Newton's Newton's 3 laws. But when we take an aggregate perspective, then the system becomes too complicated to describe just in terms of the 3 laws. So then people figure out some additional frameworks like thermodynamics that borrows a lot of other concepts, for example, temperature and pressure, and this kind of macroscopic concepts. They're using this kind of macroscopic concepts to understand the sense system that could otherwise be described by the traditional mechanical laws. So natural language understanding is a similar framework. So when the AI systems become increasingly complicated, we need to use a set of different terminologies and concepts to understand what happens inside the AI systems and what those AI systems can and cannot do. And these are the natural language processing systems. So the abilities that we are interested in is the system's ability to understand languages. So according to Jorovsky and Martin, natural language understanding is considered a holy grail problem of NLP. So there is the hierarchy of humans' understanding towards languages, which partially answers your question. So you have seen this kind of hierarchy in the introduction slide of the CSC 401. So on the most surface level, there is this understanding about the syntax of language. So we know that if, for example, the subject is in plural form, then the verb should also occur in the corresponding forms. So that we can achieve the subject-verb agreement. And there's also the structures within the sentences. Like usually the structure of sentence follows a subject and a verb, predicate, or an object. And in one level higher, there is the semantics. So you know that the symbols actually correspond to some concepts that in your mind. And in this way, the symbols have some meanings. And when putting the symbols together, you are able to understand the meaning of the sentences and even paragraphs. But beyond that, the paragraphs do not consist of standalone sentences. The sentences contain, when the sentences are put into the paragraph, each of them have some corresponding roles. And I will provide some examples in the next few slides about the discourse roles. Additionally, there is the common sense and pragmatic layers, which essentially involve some information and knowledge that exists beyond the scope of sentences. So common sense essentially involves some knowledge and information that is outside of the sentences. So when trying to, for example, understand the sentence, the elephant is too large to put into the fridge. What is it? Then you need to borrow the common sense from your own knowledge base that the elephant is too large to put into the fridge. And usually the elephant is the mammal that is much larger than the fridge. But this kind of thing is extremely hard for the, especially the deep neural network-based language models to address. And pragmatics is also very hard as well. So as an example, when setting up the computer, if I ask you, do you have a USB cable? Then it's very likely that what I mean is not just I ask you if you have a USB cable. It's just that I'm borrowing a USB cable. So understanding the difference between the meaning that is in the sentence and the meaning that the speaker wants to convey is in the layer of pragmatics. And these levels are only here to organize the tasks. And there are a lot of overlaps between the levels, and they are not mutually exclusive, and they are by no means rigorous. So also many natural language processing tasks require understanding at multiple levels. Let's say the translation problem requires understanding the syntax and the semantics, and perhaps a little bit of the discourse as well. So how to quantitatively test the understanding of the NLP systems? Currently, what people are doing is to formulate some deterministic computation problems. And most of those problems are prediction problems. So sequential tagging is a prediction problem of this type. You can formulate a grammatical error detection problem. And for example, you give the app a sentence and let the app predict if this sentence is grammatically correct. And if yes, then okay. But if no, then where does the grammatical error occur? And further, how to correct for this grammatical error? So detecting grammatical error is usually formulated as a sequential tagging question, but correcting the grammatical error can usually be formulated into a sequence-to-sequence learning problem. And sequential tagging is the form that is usually used in testing the natural language understanding. And by the way, anyone recognize which software is this? Like Grammarly, yes, exactly. Yes. So in terms of semantics, people usually try to embed the semantics into vectors, and the machines can operate on vectors which are essentially lists of numbers much easier than the way they're supposed to handle the symbols. So symbols are extremely hard for machines to operate on, but numbers are a lot easier. So usually the vector representations or the embeddings are key to the understanding of the meanings, according to many papers that build natural language understanding systems. And an example to test if the model has correctly or successfully embedded the meanings into the vector is Quora question pair. So you present a pair of questions from Quora into to the model and let the models embed and produce the vector representation of those two question pairs. And for example, and then you let the models compute the vector similarities. And if this similarity is beyond a threshold, then this machine predicts yes, otherwise predicts no. And then you can compute the accuracy that this machine recognizes that these two questions come from the same pair of Quora questions. Or otherwise, in other words, whether these two questions are paraphrases of each other, if they talk about the same meanings. So if the machine is able to correctly recognize that these two questions talk about the same meaning, then essentially we can say that this natural language understanding system understands the semantics pretty well. So any questions up to now? Okay, great. So now we are going to talk about the discourse structures. So here's a movie review on IMDb. I'm going to briefly read this. It will take around 2 minutes. So this is not a movie for fans of the usual eerie Lynch stuff. Rather, it's for those who either appreciate a good story or have grown tired of the run-of-the-mill stuff with overt sentimentalism. New line, new line. The story unfolds flawlessly, and we are taken along a journey that I believe most of us will come to recognize at some time. A compassionate existentialist journey where we make amends for our past when approaching there's a typo here, our inevitable demise. New line, new line. Acting is without fault. Cinematography, likewise, occasionally quite brilliant. And the dialogue leaves out just enough for the viewer to grasp the details of the story. There's another typo. It should be off, not OD. New line, new line. A warm movie, not excessively sentimental. Is this a positive or negative review? How many tend to think it's positive? And how many think it's negative? Yeah, it's indeed positive review. And we can attribute the polarity of this review to some keywords, for example, good story, or flawlessly, and without fault, and quite brilliant. This kind of words give the review some polarity. But beyond the sentiment, we can also recognize that these a few sentences form a holistic structure that contributes to the discourse of the movie review. So I color-coded some sentences with green, blue, red, and orange colors. And the sentences in different colors are actually talking about some different things. They have some different functionalities and contribute in different ways to the holistic discourse. The green sentences are overviews. They set the stage, and they provide some high-level summaries of why this movie review is positive, and essentially it also provides some recommendations of this movie. For example, it says that it's for those who appreciate either a good story or have grown tired of the run-of-the-mill stuff with over sentimentalism. Then the blue part comments about the storytelling, and the red part comments on the acting and the dialogue. cinematology, etc. So the blue and the red sentences are essentially elaborations. They comment on different detailed aspects of the movie, and they provide some rationales to support the claim that this movie is for example, for those who either appreciate a good story or have grown tired of the over sentimentalism. And after that, this movie review finishes with a conclusion sentence that summarizes what this reviewer thinks about this movie, one movie not excessively sentimental. So this is a summary, and it concludes this movie review. So these kind of structures are kind of easy to be recognized by humans. But for machines, it's extremely hard to tell apart that the sentences within each paragraph have actually contributed to different functionalities of the discourse. So if you, for example, type this paragraph into ChatGPT and let it produce a discourse parsing, which means that you expect ChatGPT to output some descriptions of the functionality of this kind of sentences, or like these slides have done, then ChatGPT is most likely going to write some random things that appear to make sense, but they actually do not. This is because the discourse parsing is still extremely hard for the language understanding systems to do. So discourse parsing can also be formulated into a sequential tagging problem. So you can you can give the model this whole paragraph, and also ask this model to predict the functionality of the first sentence, and let it let it choose a label between, for example, opening sentence, elaboration, and conclusion. And in this way, you can formulate the discourse parsing problem into a sequential tagging problem, a sequential classification problem. But it's still a very hard problem. Question?
So how is the SOTA, a state-of-art system, doing on this kind of tag? Like, I mean, we're doing pretty well on like post tagging, right?
Yeah. Part of speed tagging is pretty good.
For this
But
kind of tagging, how well are you doing that?
So for the discourse parsing, you can check out the Penn Tree Bank, Penn Discourse Tree Bank dataset, or PDTB. And recently, the Georgetown University have compiled a larger dataset for evaluation benchmark of the discourse parsing. It's called GUM, the Georgetown University massive corpora for the discourse parsing. Yeah, and if you're interested, you can check out the performance there. So let's take another look at another paragraph. So this paragraph is an abstract of an article that is currently pretty popular. So the name of this article, the title of this article is "Language Models Are Unsupervised Multitask Learners." As you are probably already familiar, that this paper is the paper that proposed the GPT-2. So this paragraph is also not a collection of random sentences. There is a clear structure within this abstract document. So this paragraph starts with a sentence that states the problem. So NLP tasks such as question answering, machine translation, reading comprehension, and summarization are typically approached with supervised learning on task-specific data sets. So this states the problem and also sets the stage, provides an overview of the field. And the next sentence describes the solution. So we demonstrate that language models begin to learn this task without any explicit supervision when trained on a new data set of millions of web pages called web text. So this is a summary of of that paper's solution. And then this paragraph spans a few additional sentences that describe the performance of the system. So this system performs well on the COCA dataset, and is very successful on the zero-shot task transfer, and it achieves state-of-the-art on 7 out of the 8 language modeling dataset, etc., etc. After that, the orange sentence provides a summary of the abstract. It concludes the abstract with an emphasis on the significance of this solution. These findings suggest a promising path towards building large language processing systems which learn to perform tasks from their naturally occurring demonstrations. So actually the abstracts of natural language processing articles are written in a similar way. There's usually 1 or 2 sentences stating the direction, and it explains what problem you're trying to solve and why is that an important problem. And then the abstract usually spends a few sentences summarizing the solution. So usually it's about proposing a solution that is very smart and is very highly performative, or is highly interpretable or highly reliable. The solution has a lot of benefits. And the last sentence of the abstract is essentially some additional elaboration of the significance. So it is an additional argument that tries to persuade the users or the readers to take their solutions instead of other people's solutions. So this kind of discourse structure is also can also be put together to test the ability of understanding the discourse of the natural language understanding systems. So let's come to the common sense. Broadly speaking, common sense is everything that exists outside of the context. So it is something that is not in the sentence. In the elephant and the fridge example, the common sense is the information that tells you that the elephant is usually much larger than the fridge. So this type of problem formulation is called Winograd schema challenge. And this challenge was actually proposed by a brilliant U of T professor, Professor Levesque, around 30 years ago. And in order to correctly answer what is too big or what is too small, you need to use the common sense knowledge that exists beyond the context of the sentences. So interestingly, GPT-3 DaVinci 2 model is able to understand is able to put together some part of common sense knowledge that is beneficial for solving this kind of problems. So DaVinci means that describes the size of the GPT-3 model. So GPT-3 have several different sizes, and the smallest one is called Ada, and the second one Babbage. The third largest is Curie, and the fourth smallest is, or the largest model is called DaVinci. And 001 was the original bona fide GPT-3, and GPT-3. And currently, ChatGPT is an improvement of GPT-3, DaVinci 3.5. But currently, there are some people online saying that ChatGPT runs so fast that it can't be a DaVinci model. It has to be a model that is smaller than the size of DaVinci. It has to be something like a Curie model or even a Babbage model. But I'll describe more in the last lecture, a tale of ChatGPT. So the way that I'm using GPT-3 to generate this kind of response is by prompting. So we present GPT-3 with a description of the sentence, the description of the problem. So an elephant can't be put into the fridge because it's too large. What is it? So this problem itself is the prompt, and we let it continue generation. And here's what GPT-3 writes. It says, a fridge is a household appliance that is used to store food and keep it fresh. An elephant is a land mammal that is too large to fit inside a fridge. So apparently, GPT-3 is able to put together the piece of information that it captures from the training corpora and use it to answer this question. There are some alternative ways that we can make use of the strong abilities of GPT-3. For example, we can use GPT-3 to explain to us some natural phenomena. Like we can just ask GPT-3, for example, the sky is dark, why? And GPT-3 is going to say some very interesting things. But we are going to describe them in detail in the next few lectures. So it is in the lecture of interpretability. It's called natural language explanation. Okay, question?
Sure, can you go to you're saying that the GPT-3 understood the common sense, like because it is like summarizing that the elephant is too large to fit into a fridge, because you said that elephant can be put into a fridge. You have given him that fact.
I'll be cautious in saying that it has common sense. So I'm just saying that on this instance of the problem, GPT-3 is able to put together the common sense knowledge that is needed to address this problem.
It extracted that information from this sentence.
From
the sentence you've given it.
The common sense is extracted from its memory.
Yeah, so
Its memory is not in the.
Just assuming, for example, if I say that a mouse can be fit into a fridge, I would like follow this question. A mouse can be fit. Would the elephant be larger than a mouse? Would it respond that yes, elephant would be larger than a mouse, because since we know that mouse can be fit into a fridge.
Yeah, this is a very interesting question. So the question is, if I let the model to explain a spurious phenomenon, then what will happen? And it really depends. So the observation actually depends on the model itself. So some models will say that yes, you can't put a mouse into a fridge because the mouse is too large, and it tries hard to hallucinate something that can sort of explain the spurious phenomenon. And some other models like ChatGPT would just say that no, the described phenomenon is incorrect. A mouse is actually able to be put into a fridge because it is small enough. So it really depends on the behavior of the model. And actually this type of spurious phenomena is actually used as a special engineered edge case to test the behavior of the large models.
I think the knowledge, in recent years, they propose that the knowledge representation and the reasoning should also be added as another way for the language model to understand it, because LLM doesn't really understand anything, just predicting possible next words. Right?
Yeah, exactly. Actually, Yang LeCun actually recently published a paper saying that augmented language models, the large models should be augmented with the external knowledge bases and the like other things that you mentioned, so that they potentially could have stronger reasoning abilities and some other abilities. So the reasoning abilities are something that is sort of relevant to the pragmatic knowledge, and being able to use this knowledge is another step ahead of the understanding of the knowledge. So understanding is step one, and being able to use the understood knowledge is step two, and it's usually much more difficult. So the understanding for pragmatic is also a very difficult problem. So personally, I come from a high context culture. Many of the East Asian cultures are high context. So what we say are only the tip of the iceberg, and we need to infer make a lot of inference on what this speaker is trying to say, and then a few years later, I came to North America and realized that North America cultures are very low context. So people try to cram in whatever they want to say into the sentence explicitly. So a lot less inference is needed to be done to communicate in English. And this kind of things impose a challenge for understanding the pragmatics. So when we present the same sentence to different people, they might have different effects, and people might perceive the sentences differently. The sentences have different perlocutionary effects. But when formulating the kind of problems to test the pragmatic ability of the models, we usually give them very simplification of a lot of very simplified assumptions. And one of the assumptions is that everyone essentially is the same. So there is a static label for each post on Reddit. So this assumption allows us to formulate the identification of the political stance on Reddit, for example, assignment 1, into a classification problem. So this is, as a summary, so this is just a simplification. This simplification does not usually hold true in the real world. So let's talk about some types of systems to build natural language build natural language processing systems. And depends on which part of the system is used to understand language. We can briefly, roughly describe them into 3 types: feature-based, embedding-based, and deep neural network-based. So we'll do a brief comparison of these systems. So feature-based natural language understanding systems carve out a lot of engineering features and then use a machine learning model to try to predict something based on the engineered features. So the feature engineering part essentially is responsible for the understanding of language. The engineers who engineer the features contribute to most of the understanding of the language. So you can say that how much artificial word in the engineered feature, how much intelligence there is. So this is a joke, but my point is that the feature-based natural language understanding systems usually are not really strong in understanding, and usually it's very, very, very time-consuming to compute the features. So later, people start to use the embedding-based natural language understanding systems. So you are familiar with Word2Vec and GloVec and other types of word embeddings. So these types of natural language understanding systems first embed the text or other multimedia data using some embeddings, and then plug in those embeddings into some machine learning models like convolutional neural networks, or recurrent neural network, long short-term memory, or even transformers, and they get some prediction result. So in this type of systems, the embedding handles the low-level features, and it is not really necessary to carve out engineering the features. So the embedding is assumed to take care of the understanding, and after that, the machine learning model, usually a neural network or the conditional random field, takes care of the task-specific predictions. So the understanding is taken care of in the embeddings. More recently, people have figured out a new methods for building the natural language understanding systems, which is termed deep neural network-based understanding systems. So they first pre-train a language model, for example, BERT or Elmo, and this kind of language models are trained on massive corpora, and the pre-training tasks are very irrelevant to the downstream tasks. Some of the pre-training tasks include masking out some words and predicting what that words are, or predicting the next sentence, or predict the next word or next tokens. These kind of tasks are very distant supervision signals, and it is assumed that by pre-training on this kind of tasks, the language model understands a large part of the language. So now we have a language model that sort of understands the language, And then we can use these models to make some prediction results based on the downstream data. And the way is usually done by a fine tuning. So you can either fine tune. So you usually attach a classification head on top of this model, and fine tune either the classification head or both the head and the model's parameter along on the downstream task data. And in recent years, there are also some methods to do parameter efficient fine tuning. So I'm not going to go into the details of parameter efficient fine tuning. The point is that you don't need to fine tune all of the parameters in the language model. You just need to fine tune the classification head and some part of the models and some part of the parameters that are either inside the model or outside of the model. So back to the deep neural network-based understanding systems. The language understanding part is handled by the large language model, the pre-trained language model. So the difference between DNN-based understanding system and the embedding-based understanding system is that the deep neural network-based understanding system is based on the deep neural network, which handles the understanding of the language. And there are a large overlap between the deep neural network-based systems and the embedding-based systems. And you can argue that the neural networks that are used to embed the text, for example, the word-to-vec embedding is also a neural network, but it's not a deep neural network. It only has one hidden layer, and it's essentially one matrix for embedding and another matrix for the output prediction. So they are not deep neural networks. So these are the subtle differences between the embedding-based systems and the deep neural network-based systems. So in assignment 3, we are going to implement deep neural network-based systems for sequence classification. I will talk about this in more details on Wednesday and Friday. So Friday's tutorial will be some walkthroughs of some coding examples. So definitely come to the Friday's tutorial. And we can compare these three families of systems along 2 dimensions: capability and controllability. Capability is usually the dimension that people usually care about the most. So capability is usually measured by accuracy. So the so-called state-of-the-art are described along the dimensions of capability. This kind of abilities include the ability to understand the syntax, understand the semantics, and understand the structures of the paragraphs or the articles. But along another dimensions, there's also another very important another very important attribute that I want to emphasize, which is the controllability. And some people also want to term this as safety or the interpretability. So the feature-based systems, although usually have the lowest capability, usually have the highest controllability, because there are a lot of well-established statistical tools to attribute the predictions of the feature-based systems towards some particular features. So that the models can be dependable, it can be accountable. And when the model predicts some result, then you can attribute the predictions back to some features. So this property is very desirable in terms of high-stake decision-making problems. For example, machine learning for healthcare and machine learning for the legal practice. In this kind of application scenarios, it's actually beneficial for using the feature-based systems instead of some more fancy deep neural network-based systems. And 1 minute. And in terms of the embedding-based systems, usually people use embedding-based systems to save the computation efforts. And if you use embedding-based systems, you don't need to allocate the computations that are enough to run a 12-layer BERT, for example. and you can just use a much smaller computation resource, so that it can run on, for example, some very small devices like your watch. Yeah, question?
Yes, sir. I'm not exactly understanding what's the difference between embedding-based and the DNN-based model. So, a transformer or a bird, they map the income word to some latent embedding. So, how is like embedding and DNN different?
So transformer models are DNN-based models. So all of them are DNN. So, sorry. So all of the models that occur out of after 2018 are essentially deep neural network-based models. So that include Elmo, BERT, GPT-2. These kinds of models are all deep neural network-based models. So the key attribute of DNN-based models is that the whole of DNN contribute to the understanding of language. So
yeah. So my question is like, how is because DNN always mostly use embeddings in their model. So
yeah, so embedding is just one part of the system, and embedding is not the most important part that handles the understanding in the deep neural network-based systems. So there are, let's say we are considering a system based on BERT-based. So BERT-based has 12 layers instead, in addition to the embedding. And the embedding essentially just embeds the token and the position and the sequence segments. So BERT-based has 3 types of embeddings, and they add them up together. But this kind of embeddings do not handle much of the meaning of the sentences. The upper layers, the 12 layers on top of them handles the majority of the language understanding. So that's what I mean by all of the layers in the deep neural network-based system contribute to the understanding. But in the embedding-based systems, the embedding handles the understanding, and
one layer of embedding-based system.
Just one.
All of it.
Yes. So in the future, we should have some NLP systems that have both high capability and high controllability. Augmented models might be the way to go, but who knows? So there's also the benchmark saturation problem, which essentially describes that in AI, the performances of the models are catching up to all humans' performances, and the speed that they are catching up has become increasingly faster. So this is an interesting trend. I'm not saying that it's a good trend or a bad trend, but it is an interesting trend. So there are some philosophical discussions here. If you are interested, you can check it out. The simulator hypothesis and Merritt's room. So Merritt's room essentially says that the large language models are trained only on the text. So although the large language models have access to all the text in the world, they don't really understand everything in the world. Actually, they cannot ground the concept onto the real world, and they need to be provided with some additional knowledge about what happens in the real world in order to complete this gap. So by the end of this lecture, you should be able to describe natural language understanding, which is a metaphorical term that assesses the abilities of the models. And there are 3 types of systems: feature-based, embedding-based, and deep neural network-based. Sometimes some of the systems are better than others. And yeah, come to the lectures on Wednesday. We'll continue describing how to build natural language understanding systems.